So tonight's speaker is Warren Allmon, and why we should all know and care about Antarctica, and Warren is PRI's director. 2 weeks from tonight, we will have Regina Asmutis-Sitvia from the Whale and Dolphin Conservation North America, talking about saving the whales who can help save us. And our last session on May 9th will be Unlocking the Ocean's Mysteries with the JOIDES Resolution, with a panel of educators who have sailed on the premier ocean-going research vessel in the world that is about to be retired. And with that, I'm going to hand it over to Warren and say, go ahead, take it away, Warren.
Thank you, Don. So I have to push the right button, right, Don?
That's right.
Okay. Did I push the right button?
You did. Excellent work.
Awesome. Okay, my work here is done. Thank you all for being here, and thank you, Don, for, as usual, organizing this series. I have a pretty great job. Some of you know, I have two jobs. I'm the director of a natural history museum in Ithaca, which is not part of Cornell, and then I'm also a Cornell professor. And so those two things intersect a lot. And so tonight I'm going to tell you about some of those intersections. One of them was a serious bucket list item on my part. I've always wanted to go to Antarctica, and I got the opportunity to do that as one of two Cornell faculty as part of Cornell's Adult University, which is one of Cornell Alumni Affairs programs to get alumni and friends of the university out doing interesting things around the world. And I've been fortunate enough to do things with them for a long time. And they finally got me to Antarctica in January. And so that was my first trip, but I've had a lot of experience with Antarctica from afar, and I've been teaching about it for several decades. And as you'll see, our museum holds one of the world's largest collections of fossils from Antarctica. And so that kind of added to my motivation to want to be there. But of course, more broadly, in my business of teaching Earth history and paleontology, you can't do that without knowing something about Antarctica. And these days, you absolutely cannot think or write or teach or deliver public programming to the world about the Earth unless you think about Antarctica. And that's really my message tonight. So I've called this Why We Should All Know and Care About Antarctica on purpose. I being a geologist, I of course naively think that everybody thinks the way I do, and that's of course not true. And for most people, Antarctica is a little white band across the bottom of the world map, and it's out of sight and out of mind. And I hope that by the end of tonight, you will, if you don't already, think that is really important to change. We should all know about it, and we should definitely all care about it. So with in the spirit of realizing that most people don't think about Antarctica every day, I thought that I'd provide some basics. So the first thing is that Antarctica is at the bottom of the world, and that means that east and west don't mean the same thing down there as they do in the rest of the world, and that takes some getting used to when you're thinking about and navigating in Antarctica. So maybe you all know this, but I really hadn't completely internalized it until I went down there. Antarctica is naturally divided into two pieces, and literally those were two pieces in the geologic past. Today they are physiographic regions that are really very distinctive, and you'll hear more about that in a few minutes. They're called West Antarctica and East Antarctica, which doesn't make any sense, again, at the bottom of the world. So the way to think about it is that West Antarctica borders on the south part of the Pacific Ocean, and East Antarctica borders on the south part of the Atlantic and Indian Ocean, which is roughly, east and west. So that's the terminology. The Antarctic Peninsula, where we're going to spend most of our time tonight, is part of West Antarctica. The Antarctic Peninsula is the piece of Antarctica that is closest to the rest of the world. It is relatively close to the tip of South America, Tierra del Fuego. It is only 600 miles. That is a very small fraction of the other distances between Antarctica and the rest of the world, which are measured in thousands of miles. So most people who go to Antarctica, which is an increasing number of tourists and scientists, leave out of South America. Most U.S. scientists leave out of New Zealand for logistical reasons. But Antarctica is a long way away in any case, and that it takes some getting used to think about kind of where it is relative to things that we're more familiar with. So East and West Antarctica, remember that. Please also remember that Antarctica is absolutely gigantic. It is not the little white band at the end of the map. It is the size of the United States, including Alaska, or the lower 48, including Mexico. It is a huge place, and it is still largely unexplored. It's obviously completely, largely uninhabited, with the exception of a few hundred people. And so it is the last place on Earth where people do not permanently live. And that's obviously incredibly important to remember in our thinking tonight. It is, of course, famously covered mostly with ice. 98% of Antarctica's land surface is covered by ice. It's pretty remarkable, actually, given that 98% of it is inaccessible, that we know anything at all about Antarctic geology. But we do know a fair amount about it from that 2%. I will talk a little bit about that tonight. But it is 98% covered by ice. And it has a bunch of distinctions. You all probably know that it's the coldest place on Earth, but it's also the driest, the highest, and the windiest place on Earth. So when you boil all of that down, when you consider everything I've just said to you, Antarctica is almost literally a different world, and I don't mean that just metaphorically. It is an extreme place. By every measure of Earth conditions, Antarctica is different, and that's an important part of our story tonight. Here's just some factoids, which people like. Some temperature maps in the winter and the summer. Winter is really winter in Antarctica. It's just about the end of summer right now in Antarctica, and about to be winter. So look at the map on the left. The coldest recorded ground temperature on Earth was recorded in central Antarctica, which is minus 135.8 degrees Fahrenheit. That is extremely cold. And the average surface temperature in Antarctica is still well below what we would all consider comfortable. And so Antarctica is a very extreme place by every measure. It is so extreme, it is so different that NASA declares it, treats it like the closest thing to Mars that we can actually go to. And so that I find that fascinating. I find it fascinating that there is a place on Earth that is almost similar to Mars. The picture on the left are the famous dry valleys near McMurdo Station, which is the biggest scientific research station in Antarctica. The dry valleys, it hardly ever precipitates there. There's no snow, there's no precipitation, and it's very, very cold all the time. And so NASA actually studies that and tests equipment there. That will become increasingly important as we gear up to go to Mars in the next few years. And so literally NASA treats Antarctica as a simulation of Mars. On the right-hand side, you can see some statistics about that. This is just a graph of mean temperature on the vertical scale and precipitation on the horizontal, and you can see the word Mars down there at the bottom. So the Antarctic interior and the dry valleys are literally very, very close to Martian conditions, and I find that fascinating. So when we're talking about Antarctica, keep in mind that it really is the most different place on Earth you can possibly go. And I emphasize that because what I hope to convince you of tonight is that if you aren't already knowledgeable about this, is that Antarctica is so exceptional and so extreme and so different and so strange that we tend to discount it if we ever think about it at all. It's this foreign place, and where ice and penguins are. And all that's true. But at the same time, Antarctica is, in a way, one of the most representative places on Earth for what is happening to the Earth now and what is going to happen to it in the coming century. And so that's my title today: is why you should know and care about Antarctica. Isn't because it's this amazingly wacky place and extreme in all Earth standards, but because it isn't, but because it's telling us something about what is actually going to happen to the rest of the world. So actually, if you want to hang up now, you can leave now, because that's really what I was going to tell you. Okay. So some basics about the ice. Everybody thinks about ice when you go to Antarctica, and ice is everywhere, and it is obviously the dominant feature in Antarctica. So these numbers don't really mean anything, but they're you have to put numbers on things. 14 million square kilometers. What the heck does that mean? That's 5.4 million square miles covered by ice. So imagine all the 48 states plus most of Alaska covered by ice. That ice, if you measure its thickness and calculate its volume, turns out to be 6.4 million cubic miles of ice. I always think about that when I'm taking ice cubes out of the freezer. Think about what 6.4 million cubic miles of ice looks like. The average thickness of that ice is 1.2 miles, the average thickness of the ice sheet over the surface of the continent. So the next time you drive a mile, think about that was the thickness, that's the average thickness of the ice over the Antarctic continent. 90% of all the ice on Earth is in Antarctica. And that, if that melts, which a lot of people talk about, if all of it melted, then global sea level would go up 190 feet. Nobody's thinking that that's going to happen anytime soon, but it's a really important number to remember, that there's enough water in Antarctica to flood basically every coastal plain in the world. And Antarctic ice holds 61% of all the fresh water on Earth. So the significance of these numbers is really not that it's an extreme place, but that it's actually a really central place. If you think about water on Earth, particularly fresh water, Antarctica is a really important place. So it's important, if you're not familiar with glaciers in Antarctica, to remember that there's three kind of big flavors of ice in Antarctica. Three big kinds of ice. There are lots of words for ice. There are dozens and dozens of words for ice in Antarctica. It's like the old story, which isn't true, that Inuit peoples have lots of names for snow. In the Antarctic, scientists have dozens of words for different kinds of ice. But there are three big categories. The first, which is the one that I just talked about, are called the ice sheets. And these are the big glaciers that cover the continent. It will be important for our story tonight to distinguish between the ice sheet that covers the West Antarctic, covers West Antarctica, which is abbreviated the WAIS, the West Antarctic Ice Sheet. And then that's to be contrasted with the East Antarctic Ice Sheet, which is much bigger, because East Antarctica is much bigger than West Antarctica. An interesting part of the story, which we will come back to, is that the West Antarctic Ice Sheet is referred to as a marine ice sheet, and that's for a really interesting reason. It's because much of Western Antarctica is actually below sea level. So what does that mean? It means that if you got rid of all the ice, you would see that West Antarctica isn't a continent completely above sea level. It would be an archipelago. And that's going to be important to our story later on. East Antarctica is topographically higher. So all of the ice on the East Antarctic ice sheet is referred to as a terrestrial ice sheet because it's above sea level. So the point of the story is that the East Antarctic ice sheet and the West Antarctic ice sheet are two very different things, and that'll be an important part of something we talk about tonight. Okay, so that's most of the ice, but there are also two really important other kinds of ice in Antarctica. One is the ice shelves. The ice shelves are pieces of ice that are coming off of the glaciers that cover the land, but they actually go out across large swaths of ocean and sit there and float there. Occasionally, well, pretty consistently, but occasionally if you stand there and look at them, they break off, and we call those pieces that break off icebergs, and those are the ones that you read about in the news that are floating out into the shipping lanes. Big icebergs come mostly from ice shelves. There are two really big ice shelves in Antarctica. The Ross Ice Shelf, which in the picture on the right is kind of at the center bottom there. That is where McMurdo Station is. If you have ever read anything about McMurdo is the only thing that passes for a town in Antarctica. It's the main U.S. base. It's located to the lower right of the Ross Ice Shelf. And so a lot of people know about it because scientists fly in and out of McMurdo. The Filchner-Ronne ice shelf is in the upper left here, and that is in the Weddell Sea. The Ross ice shelf is in the Ross Sea. The Filchner-Ronne ice shelf is in the Weddell Sea, and that's closer to the Antarctic Peninsula, where we're going to be spending most of our time tonight. So those are really huge ice shelves. They're the size of France. They're really big. And then there are smaller ice shelves that we'll talk about in a second. And then the final category is sea ice. And sea ice is ice that breaks off and is floating around Antarctica. It's connected in the winter, it detaches in the summer. Sea ice is really important. And the map that you're looking at here on the right is a map of Antarctica in the winter when sea ice is at its maximum extent. So when you think about all of the ice in Antarctica, which we're going to talk about tonight, it comes in these three categories: the ice sheets, which are on the continent; the ice shelves, which are floating but connected permanently to the ice to the continent; and the sea ice, which is kind of intermittently connected to the continent. And here's a cartoon to show those three kinds of ice. The ice sheet connected to the ice sheet, but it's sticking out, floating on the water. And then sea ice, which is breaking off, frozen in the winter, breaking off in the summer, off of the ice shelf. Note that there is water under the ice shelf. That's going to be important when toward the end here. Here's a picture of a really small ice shelf. It's only the size of New England. And it's the Larsen Sea ice shelf. And on the map in the lower left, you can see the Antarctic Peninsula there, and it's attached to the land. And you are looking at a picture there on the right of the edge of the Larsen ice shelf. And just to give you some sense of scale, the edge of that ice shelf that you're looking at is 300 feet tall. So this is a really big piece of ice. And the red dot there in the upper left shows you where we are. So that's what ice shelves look like when you get to the edge of them. Okay, so that's ice. So a big part of what we're going to talk about tonight is oceanography, because Antarctica is surrounded by ocean. That ocean is not one of the oceans that I learned about in school. You know, we all learn about the number of continents and the number of oceans. I never learned that there was an ocean called the Southern Ocean, but it's a really important concept. The Southern Ocean is just what it sounds like. It's the southernmost part of the Atlantic, the southernmost part of the Pacific, the southernmost part of the Indian Ocean. And it is not part really oceanographically of any of those oceans, as we'll see in a second. So it's really important to point out to people, even little kids learning their geography, that there is this other ocean that they haven't heard about called the Southern Ocean. It's 10% of the world's ocean. It's a big deal. It surrounds Antarctica. And it's a major part of the plumbing of the world ocean. The big important current that operates in the Southern Ocean is something called the Antarctic Circumpolar Current. And it's probably the most important geographic feature we're going to talk about tonight, other than Antarctica itself. Because the Antarctic Circumpolar Current has extraordinary properties. And this is one reason that everybody who teaches Earth history at any kind of a higher level has to know something about Antarctica. It's because the Antarctic Circumpolar Current is, as we will see, responsible not just for the current condition of Antarctica, making it cold. It's responsible for a huge amount of the oceanography of the world. And that's really important for us to know. It's important for you to know if you want to know about oceanography and want to know about anything that happens in the world ocean, but it's especially important for us to know if we're interested in what's going to happen to global climate as we go forward. It's the longest and strongest ocean current in the world. So when you're thinking about the Gulf Stream, this is several times larger than the Gulf Stream. It flows clockwise around the, if you're looking at the South Pole, it flows clockwise around Antarctica. And it does that faster than any current in the world. And incredibly importantly, it insulates Antarctica from warmer water that is coming from lower latitudes. Now, remember, we're in the southern hemisphere here, so low latitude is up to the north. The circumantarctic current spinning around Antarctica keeps warm water from infiltrating to Antarctica from the north. That means that warm water doesn't get to Antarctica from lower latitudes and potentially warm up the continent. If you still don't think that's a big deal, always remember that the reason it doesn't snow in England very often isn't because of England's latitude. The reason it doesn't snow very much in the British Isles is because of the Gulf Stream. So moving water around and moving heat around in the ocean is incredibly important for continental climate. And we'll talk more about that as we move along tonight. So the circumantarctic current is just really, really, really important for Antarctica and for the rest of the world. Okay, at the edge of the circumantarctic current is something called the Antarctic convergence. And this is a little bit geeky, a little bit more geeky, but it's really important because the Antarctic convergence is where water from deep in the ocean comes to the surface, and water from the surface goes down deeper into the ocean. And why is that important? Because that stirs the pot. That brings nutrients from the bottom of the ocean up to the surface, up to the photic zone, and that is why the Southern Ocean is the most productive ocean in the world. That's why there's so much living in the Southern Ocean, even though it's very inhospitable and very cold and very turbulent. The Southern Ocean is the most productive ocean in the world because of this thing called the Antarctic convergence, where deep water brings nutrients up from the deep sea and feeds all the organisms and produces all that biological productivity. And then the last really big thing that you need to know about, that everybody needs to know about Antarctic oceanography, is something called Antarctic bottom water. This sounds like really in the weeds here or arcane, but it's really important. Because Antarctica is so cold, water that gets chilled in Antarctica sinks. And that water has to go somewhere when it sinks, so it moves northward. It sinks because it gets more dense. When water gets cold, it gets more dense, it sinks, and it starts moving. And when it moves to the north because it couldn't move to the south. And that further stirs the pot of the entire world ocean. And when I say stir the pot, I literally mean it stirs bottom water across the world ocean, particularly in the Atlantic, but also in the Pacific. And that brings nutrients up from the bottom of the ocean. Why is that important? Because food sinks in water. And if there wasn't something bringing food up from the depths to feed things that live in the sunlight, then the oceans would be bleak and empty places. So the Antarctic bottom water is incredibly important for the productivity, meaning the food, feeding everything that lives in the world ocean. So if there wasn't as much Antarctic bottom water, as we will see there used to not be as much, if there wasn't Antarctic bottom water, or should in the future Antarctic bottom water ever decrease, that would have major complications, catastrophic complications for the world's ocean biological productivity. Okay, that's what that said. And here's a cartoon to show you what I just said. Here's a cross section, and the continent of Antarctica is on the right, north is to the left, and so there is this circumantarctic current spinning around, going kind of away into the screen here. There's circumpolar deep water, and below that Antarctic bottom water, that green layer, which is sinking because it's cold, and that green layer is going to travel all the way up, believe it or not, all the way to the Arctic Ocean. And so it will stir the pot and bring nutrients ultimately into the world ocean. Okay, I love this diagram from the British Antarctic Survey. it's just a brilliant diagram. If you like maps, one of the fun things to do is play with map projections that you've never seen before. Um, if you're an American, you probably grew up with North America in the center of a world map, which has all the weird consequences, like India is on both sides or cut in half, stuff like that. And people in Australia love to put Australia at the center of world maps, and it's very disorienting. This is Antarctica at the center of the world's ocean. And that's one of the points I want to make tonight, is Antarctica is literally, figuratively, and mechanistically at the center of the world ocean. So we are in the very upper left of this diagram. The Arctic Ocean is in the very top of this diagram. It's disorienting, right? It's a very unfamiliar place, very unfamiliar way to look at the world ocean. But from the point of view of the world's ocean, this is how the ocean works. Everything spins around Antarctica and then gets redistributed. And once you realize that, at least for me, you start thinking about Antarctica in a really different way. Okay, so that's the introduction. So I couldn't talk tonight without showing you some pictures of my trip, because it was as it was supposed to be, a life-changing trip. And I really didn't see very much of Antarctica at all. We just went to the north part of the Antarctic Peninsula, and that was it. So you're going to see a couple pictures here, and this is not really Antarctica. This is just the edge of Antarctica. And even though it's just the edge of Antarctica, it's a really different place than you've ever been. And that's what I picked these pictures with that in mind. So this is the seaward edge of a glacier. So it's moving towards you, away from the land. You see some land down there at the bottom. It's about 500 feet tall. And you see all these cracks. The cracks glow this amazing aqua blue, which is telling you something. It's not just pretty. It's telling you about the density of the ice. And the density of the ice controls the color of the ice. And I mention that because you start thinking in a completely different way about ice when you visit Antarctica, because everything is about snow and ice there. And so you start thinking really hard about how ice forms, how ice behaves, how ice acts. And you start realizing how ice is the geological force in Antarctica. And it's not just, a cold thing that's on top of the ground. So I just love this color. And actually, those of you who've been to the Museum of the Earth in Ithaca, we took great pains to make sure this beautiful blue color is inside our fake glacier, because I had visited Argentina and seen a glacier there, and we came back and we were building that exhibit, and I said, we got to get that color right. It's a really amazing color. This just shows a sea surface. The reason this is important is there are about 6 different kinds of ice here that have names that I can't remember. But if you, and they all form on daily cycles, weekly cycles, monthly cycles, annual cycles. The ice is constantly changing, constantly moving, constantly shifting, and constantly having different colors and textures. It changes on I don't know, minute by minute, hour by hour basis. And this shot also shows how ice just completely dominates almost every landscape in Antarctica. Icebergs are an endless source of fascination in Antarctica. You are looking at a flat iceberg here, which tells you that it broke off of an ice shelf. If you see funny shaped, kind of odd shaped icebergs that aren't flat, those may have calved off of the front of a glacier. But big flat sheet like icebergs like this, the really big ones that you read about in the news, are broken off of an ice shelf. Again, this is about 200 feet high, and its highest point there on the left-hand side. And you also see a cave there in the center. Of course, they're melting when they fall in the ocean. They're melting, and the meltings, and when they melt, they change shape. And when they change shape, they flip over or sink on one side. And so the shape of icebergs is constantly evolving. And here's some of this. This is called pancake ice. Pancake ice is a combination of snow. Even though we were there in the summer, it was snowing all the time. Pancake ice is a combination of snow mixed with frozen seawater. That is, if it stays cold, it will eventually develop into pack ice. But this is this is an early morning version of pancake ice that will mostly melt by the afternoon in this case. Here are some icebergs that are in late stages of deterioration, and you can see the number of shapes that are involved here. So you're looking in the distance at ice sheet, and you're looking at small ice shelves, and you're looking at small icebergs. Actually, you're not, because Antarctic specialists will not allow you to call it an iceberg if it's smaller than a kilometer or two. This is a bergy bit. I'm not making that term up. This is a bergy bit. And this is a panoramic view of this little bay that we were in. This is our crew declared this the best weather they'd ever seen in Antarctica. It never does this, apparently. Okay, so isn't that amazing? Is the colors, the light, the ice. It was roughly 20 degrees Fahrenheit when those pictures were taken, not very cold. And you say, wow, Antarctica is really something. Okay, I just wanted to emphasize that I'm not showing you pictures of real Antarctica, because I didn't get to see that. I wanted to show you pictures of real Antarctica. This is the South Pole. It's not like the peninsula where we visited. The peninsula is like visiting Florida and think you visited, Nebraska or Alaska or New York. This is the South Pole, where there's no ocean to moderate the temperature. The ice is 2 kilometers thick, and that's where it gets to minus 100. It gets to minus 100 every winter. And people who overwinter at the South Pole have all kinds of traditions associated with it going to minus 100, including stripping naked and going outside. So I show you this one picture. This is part of the U.S. base at the South Pole. I show you this picture just to remind you that everything I'm showing you about the Antarctic Peninsula is really minor stuff, really not extreme by Antarctic conditions. Okay, so that's it. That's an incredibly inadequate overview of Antarctica. So really, one of the things I wanted to talk to you about tonight, the reason that I have always been interested in Antarctica, is how did it get that way? And I'm recycling some slides here, literally, that I use every year teaching Cornell undergraduates Earth history, because it's that important. Teaching people, general geology students, how Antarctica got this way is absolutely essential to understanding Earth history. So let me show you the slides I show Cornell undergrads. So here's the story, and they have to know this. This is looking at the South Pole. This is kind of looking from the point of view of the South Pole at the world over the last 65 million years. So the globe in the upper left is the world, is the southern hemisphere 65 million years ago, at the end of the Cretaceous, when the dinosaurs, the non-avian dinosaurs, have just died. What do you notice that's different? You notice that South America and Antarctica are connected, and Australia and Antarctica are connected. Then you go to the right there, the second diagram, and you'll notice that Antarctica is beginning to split off from Australia, forming the Tasman Strait. And that's really important, because now deep water can move between Antarctica and Australia. So Australia has now become a separate continent. But notice that Antarctica and South America are still connected. That doesn't change until about 35 million years ago. About 35 million years ago, something we now call the Drake Passage forms, named after Sir Francis Drake. The Drake Passage is the piece of water that is about 600 miles wide that separates today Tierra del Fuego in South America from the tip of the Antarctic Peninsula. And that's the closest land, that's the closest land in the rest of the world to Antarctica. That's why tourists go to Antarctica by sailing out of South America instead of South Africa. Why is this important? This is important because the formation of the Drake Passage is the origin, we think, of the Antarctic circumpolar current that I mentioned a minute ago. And here's a cartoon. Undergraduates like color, so I try to use colored cartoons. Here's a cartoon to show that more clearly. Before and after the formation of the Drake Passage. So before, Antarctica is still at the South Pole, so it's a chilly place, but it's not anywhere like Antarctica today. There might have been some glacial ice on Antarctica before 35 million years ago, but there wasn't much. So the formation of the Drake Passage is a big deal in Antarctica. We think that it is the reason Antarctica became quite abruptly widely glaciated. The Drake Passage is usually shown as these maps with little arrows, like you see here, which of course is misleading. Here are two, these both show kind of the same thing in different colors, but I find these really interesting. These are also, in some sense, artificial images, but they much more accurately show what ocean currents really are. Ocean currents are not arrows. Ocean currents are eddies. They are streams of eddies, and that's why I like these. These kind of show what the circumantarctic current really looks like. So again, it's this clockwise thing that goes around Antarctica after the formation of the Drake Passage, and separates it from the rest of the world ocean. Okay, what happened when that happened? This diagram is pretty much the standard, most widely used representation of global average temperature of the world's ocean over the last 70 million years. So at the bottom this is roughly the same time span as those circular maps I was just showing you. So at the bottom is the end of the Cretaceous, 65 million years ago, and at the top is the present day. To the left is cold, to the right is warm. And where the blue arrow is at a roughly 35 million years ago is we think, the date of the opening of the Drake Passage. And I'll show you why we think that in a second. And notice this graph of temperature. The graph of temperature right at about 34, 35 million years ago has a real dash to the left. And that represents cooling dramatically, abruptly cooling temperatures in the Southern Ocean. And we think that is the event that leads to the massive increase in glaciation in Antarctica, and thereby does all those things, creates all those things that I was mentioning a few minutes ago. It refrigerates the entire world. It causes the creation of Antarctic bottom water. It causes the Antarctic convergence, which causes upwelling of water that creates new productivity in the Southern Ocean. It insulates Antarctica, refrigerates Antarctica, which produces a positive feedback cycle, which continues to refrigerate when ice grows. When ice reflects back sunlight, then things get even colder, positive feedback loop. This is a really, really big event in world geological history because what it does to the rest of the world. It's not just something that happened in Antarctica. And we think it happened because the South America separated from the Antarctic Peninsula. Okay, why are geologists so clear about this? Don was mentioning at the top a talk that's coming up in this series from folks that sail on the JOIDES Resolution, which is the major oceanographic research vessel in the world. So what you see in this tan box, those colored vertical bars there, those are deep sea cores that get drilled by the JOIDES Resolution and its predecessor ships in the Southern Ocean. So the ship parks in the middle of the Southern Ocean in an amazing feat of engineering that has been compared to dropping a piece of wet spaghetti about 5 feet down and putting it in a little tiny hole. They drop a long rod down and they drill a hole in the ocean floor and they pull a core of sediment out. And when they pull that core of sediment out, they can date it, they know how old it is, and they can know what the sediments consist of. And the point of this figure that you see here with the green and the blue and the white bars there is that notice where the dark blue color appears. The dark blue color represents what's called glacial-marine sediment, which means sediment that is in the ocean, but clearly came from a glacier. And the first time glacial-marine sediment shows up in the Southern Ocean in these deep sea cores that come from the bottom of the ocean is right about 35, 34 million years ago. How did it get there? Well, the picture on the left is an example of how it got there. When glaciers travel over land, they pick up rocks, they pick up sediment. And when they get to the ocean, they, as we've talked about, they fall off into the ocean and they eventually melt. And when they melt, they drop their garbage. They drop those rocks. They're called drop stones or ice rafted debris. And so what you're looking at there is an upside down iceberg that has floated out to sea. And eventually that piece of ice there is going to melt and it's going to drop all those rocks into the ocean. And then they're going to land at the bottom of the ocean, and that will mark the presence of that iceberg. This is the forensic side of geology, right? You weren't there for the crime. You see the evidence much later. So all of that story that I just told you explains my otherwise inexplicable glee on this trip I took in January to see this ugly looking rock, actually a piece of ice. We were out in the Zodiac looking at, penguins and seals and all this fun stuff. And what am I looking at? And I'm like, oh my God, stop the boat. We got to get a picture of this. This is a dirty piece of ice, but look what it's got in it. It's got a dropstone in it, a future dropstone. That black blob sitting in the middle there is a rock that came off the Antarctic continent, carried by a glacier. A piece of ice fell off. It's now floating out in the Southern Ocean, and it's going to eventually melt and drop down. This is how we know that 34 million years ago, glaciers reached the ocean from Antarctica, signifying that Antarctica had cooled. And that's the formation of the Drake Passage, with all of its consequences. This is the Drake Passage. And I just want to tell you just one little story here about the Drake Passage. So the Drake Passage has the reputation of being the most turbulent water in the world. And everybody who works in the Southern Ocean will tell you stories about it. The Drake Passage has the highest winds, the highest seas. It is generally miserable to cross in most circumstances. The average swell in the Drake Passage in the summer when we were there in the austral summer, the average swell is 4 to 6 meters. Do the arithmetic for a second. Those of you who are sailors, that means the waves are 12 to 20 feet high. Okay, that's an average day. And this is that swell. So this is an average day in the Drake Passage. This is what our ship encountered on the way back. So this is average. I was not doing well in average, as people who are with me will tell you. And so I didn't take this. I was in bed. And so I show you this because this is a calm day, a relatively calm day, an average day in the Drake Passage. A not very average day in the Drake Passage, a not calm day, can have 50 or 100-foot swells. So it's serious water. And I tell you that story just to get you to think about that the Drake Passage sounds like, oh, isn't that nice, this little piece of water, the Southern Ocean. It's a really serious phenomenon. Okay. Okay. This is also one of my slides from my class. And this slide is showing the history of temperature in the history of the world over the last 540 million years, 550 million years. And the the blue and the pink boxes there say greenhouse and icehouse. They are the alternation between when the world is warm and when the world is cold. And I draw your attention just to the far right-hand corner there, where it says 35 in a red circle. That's the formation of the Drake Passage. So the formation of the Drake Passage has global significance on a 500 million year time frame. It kicked us out of what was the greenhouse of the time of the dinosaurs, a time when there was little or no ice on anywhere in the world, to a time where there is ice eventually at both poles. And so I show you this to show you again how Antarctica is absolutely at the center of how the world works. And here's that same temperature graph that I showed you before, but now it's on its side. The present is to the left, the past is to the right, and the little black and white cartoons at the top show you the development of ice on Antarctica. So the formation of the Drake Passage at 34, 35 million years ago is when it says ice sheet inception there. And a bunch of other stuff happens for the next 34 million years, and eventually Antarctica becomes completely glaciated. But all that started with Antarctica separating from South America about 35 million years ago. Okay, what did all this stuff do to what was living in Antarctica? So for those of you who tuned in for some paleontology, this is your moment. This is one of the least glaciated spots in Antarctica. This is a little place called Seymour Island, a tiny spot of land on the very, very tip of the Antarctic Peninsula that is one of the world's great fossil locations. If you know anything about paleontology, you know that the Cretaceous Paleogene boundary is when the non-avian dinosaurs go extinct. That's the yellow dotted line that you see in the middle of this picture. Seymour Island has one of the world's great places to study the end of the Cretaceous, and lots of paleontologists and earth scientists go there to do that. More about Seymour Island in a second. It's not the only fossils in Antarctica. Here's the only story I'm going to tell you about Antarctic exploration, which is its own subject that's fascinating. The gentleman in the upper right is Robert Scott, the British explorer who led the doomed expedition to try to beat Roald Amundsen to the South Pole. He failed. Amundsen won, discovered the South Pole, got to the South Pole first. Scott had to turn around, and basically he knew he was doomed. He knew he wasn't going to make it. He left all these journals and so forth. All of his team died. But here's what an amazing, you might have other adjectives for him. Here's what a kind of guy he was. He knew he was going to die. But he wanted to make sure that he did something worthy of the British Empire. That's how he put it. And so he collected as many rocks as he possibly could on his way to his doom, on his way back from the South Pole. And the rock you see on the left is the very first rock ever brought back from Antarctica that had fossil leaves in it. He collected it just a few days before, or about a month before he died. And it eventually made it back to the Natural History Museum in London, where it sits today. Why is that important? It's the very first time that humans had evidence that Antarctica was once not glaciated. And this exact rock was quite heralded at the time. Everybody was the British Empire was remembering what a hero Robert Scott was in his martyrdom. But this rock got a lot of attention from scientists because it was the very first evidence that Antarctica had not always been glaciated, because Antarctica doesn't have any trees today, and this rock clearly has fossil leaves in it. Okay, back to Seymour Island, where there are more fossils. This is what Seymour Island looks like. It's at the very tip of the Antarctic Peninsula, next to a bigger island named James Ross Island. This is the mecca for paleontologists, many paleontologists in Antarctica. It has this area, these two islands have everything. They have dinosaurs, they have whales, they have mammals, they have the Cretaceous Paleogene boundary. It's really a paleontological wonderland. Here's what it looks like if you're a paleontologist on Seymour Island. There are places where the fossils pave the surface. It's an amazing place. There are a huge density of fossils. I know all that, even though I've never been there, because PRI here in Ithaca has the world's first or second largest collection from Seymour Island. And here's what they look like. These shells are about 36 million years old, from this little island off the Antarctic Peninsula. And they tell a very different story than the environment today. These kinds of animals do not live in Antarctica today. Hero in this little story, this is gentleman here. This is Bill Zinsmeister. Bill Zinsmeister's still alive. He is an emeritus professor from Purdue University in Indiana. He spent his entire career, very illustrious, long career, collecting fossils at Seymour Island. And you see him posing very ceremoniously here with a Purdue banner. surrounded by these beautiful ammonites, all from Seymour Island. So when Bill was getting ready to retire, he gave us his collection. And that's why we have this amazing collection. And so the fossils that you're looking at here come from the PRI collection, courtesy of Bill Zinsmeister. The highlight of that collection is this fossil that you see right here. I refer to this as a trombone that used to have a squid in it. It is an ammonite. Ammonites are distant relatives of modern chambered nautilus. And an artistic representation of what it might have looked like is on the right there. It's an incredibly silly looking animal. We're not really sure how it worked, but they were numerous. They were abundant in the Cretaceous of Antarctica. And this particular fossil you can see on permanent exhibit in the Museum of the Earth. Here's what the rest of the collection looks like. It's more than 7,000 specimens. The folks from the British Antarctic Survey came over, and I was dying to ask them if we really have the world's largest collection, and they winced in a kind of very distinguished British way and said maybe. So we definitely have a very, very important collection from Seymour Island, and lots of people come to study it for that reason. So that's really my primary kind of hands-on connection to Antarctica. Okay, that's how Antarctica got this way. What's going on in Antarctica today? What I want you to remember is that it's complicated. The news covers news flashes. The reality of climate change in Antarctica and oceanographic change in Antarctica is that it's immensely complicated, and that's a difficult thing to get students to understand. It's a difficult thing to get anybody to understand. I have struggled to understand it. People who spend their careers on it have struggled to understand it. It's a really important thing to remember in the next few slides here. I'm just going to give you some highlights. The overview is that Antarctica is still colder than the Arctic, but it is changing much more rapidly than we thought it was. There was a thought up until pretty recently that because Antarctica is so cold, it was not going to show the signs of climate change that we see elsewhere in the world. That turns out not to be true. So I want to talk about a couple of things here. I'm going to talk about air temperature. That's kind of the most obvious thing to talk about with climate change. The answer is that Antarctica is warming in some places, but not in others. And now we're back to West and East Antarctica. The map there is air temperature in Antarctica over the last 30 or 40 years. Antarctica is warming a lot in West Antarctica, but not so much in East Antarctica. Ice sheet. Now remember the different categories of ice? There is a lot of loss of ice sheets, meaning the ice that covers the continent. A lot of loss of ice sheets, but mainly in West Antarctica, not in East Antarctica. It's even growing slightly in a couple of places in East Antarctica. But overall, if you average the whole continent, there is a loss of ice sheets. The ice shelves, remember those? The ice shelves are changing in very complex ways. Some of them are deteriorating completely and disappearing. Others are growing slightly, but overall, the ice shelves are shrinking. Sea ice, that was the third main category. Sea ice is declining. It's very complicated to measure because it changes every season, but overall, sea ice is declining. And why am I using so many weasel words? Why am I saying maybe and partially and we're not sure? Because of two reasons. One is a scientific reason, like an actual substantive empirical thing about the world. Antarctica is a really complex place, which you've now seen. Antarctica is not a simple place. It's not a simple climate or a simple oceanography. It's a really complicated place, which is really unfortunate if we want to understand it. But then there's another logistical point, which is, as you've seen and as you can possibly imagine, Antarctica is a really hard place to work. And we haven't been doing it for very long. So we really have to understand those two things, that Antarctica is inherently complex, like it's really fundamentally hard to understand, and it's really hard to understand because it's really expensive and difficult to work there. We haven't been doing it for very long. Okay, remember all that with what I'm now going to show you. What I'm now going to show you in the last few slides is a couple of really some vignettes, okay? Research is exploding in Antarctica. There's tons of research being done right now. It's a huge source of or a huge activity for many countries, and the reason is that it matters. So I can't possibly summarize all of it here or even read all of it. So I'm just going to give you some, I think, some really highlight stories to take away. Okay, West Antarctica is warming a lot. And it's warming rapidly, and it's warming more rapidly than anybody thought. East Antarctica is not warming, and even in a couple of spots, cooling. Now, okay, you say, well, what's that about? Well, remember what I said an hour ago? East Antarctica and West Antarctica are different kinds of places. So that's not unexpected. East Antarctica is larger, higher, windier. It's got a lot of other things going on. West Antarctica is smaller, lower, has more water around it. It's a more complicated place. This is the kind of stuff that makes the news. It is true that record high temperatures, just like every place else in the world, just like Ithaca, just like the United States, just like the rest of the world, record high temperatures are happening really often in Antarctica now. And the record high temperature was just a couple of years ago in 2020 at the Argentinian base on the peninsula at almost 65 degrees Fahrenheit. So that's warm even by Ithaca standards. It's really warm. It's hot in Antarctica, and we can expect more of those temperatures on the peninsula in the coming years. Okay, now that's air temperatures. What about the ice sheet? The West Antarctic ice sheet is shrinking fast. There are lots of different ways to measure that, but the West Antarctic ice sheet is shrinking fast. Again, the East Antarctic ice sheet isn't in most places, but the West Antarctic ice sheet is shrinking rapidly. And that leads to this extraordinary paper that was published just last year, in October of last year. Scientists try to use less extreme language, but look at the title of this paper: Unavoidable Future Increase in West Antarctic Ice Shelf Melting Over the 21st Century. So these authors, and there's a couple of quotes here that I'll read to you. This is pretty extraordinary language for a scientific paper. We find that rapid ocean warming at approximately triple the historic rate is likely committed over the 21st century, meaning it's going to happen no matter what we do. No matter what happens about emissions or climate change, it's going to happen is what committed means here. With widespread increases in ice shelf melting, including in regions crucial for ice sheet stability, meaning is if ice shelves melt, ice sheets might become unstable. They continue, results suggest that mitigation of greenhouse gases now, meaning in the rest of the world, has limited power to prevent ocean warming that could lead to the collapse of the West Antarctic ice sheet. So just ponder that for a second. These are scientists saying that it is their opinion that no matter what we do, the West Antarctic ice sheet will disappear in the 21st century. And that's a remarkable thing for scientists to say. And that if that were to happen, as you've now seen, that's a lot of ice. It's not the same as the East Antarctic ice sheet, but it's an awful lot of ice. And it could happen in the lifetime of my daughter. Okay, this is both lighthearted and very serious. I just love this paper. Here is a paper by some geneticists who studied this cute little octopus that you see in the lower right-hand corner there. They did the genetics of this octopus that lives in West Antarctica, obviously in the ocean, on both the east side of the peninsula and the west side. And by doing the genetics, they reached an extraordinary conclusion. They reached the conclusion that 125,000 years ago, this is not fossils, this is just using genes, 125,000 years ago, which geologists call the last interglacial. 125,000 years ago, these populations of octopuses had to be exchanging genes over what is now West Antarctica. And the only way they could figure out that that happened, these authors, was that there was no West Antarctic ice sheet. And that's the cartoon you see there in the circle map in the center. So what does that mean? And what is the last interglacial? The last interglacial is the last time the Earth was as warm as it is now, 125,000 years ago. So what these folks say, and remember, these are just geneticists. These weren't climate scientists. They said, as far as we can tell, these little octopuses were exchanging genes the last time it was as warm as it is now. And the only way we can make that work is if there was no West Antarctic ice sheet. Translation, the West Antarctic ice sheet isn't going to be here very much longer based on octopus genes, which I find both obviously sobering and fascinating as a scientific paper. Okay. Graphs like this now come out with great regularity. This is sea ice, okay, not ice shelves, or not ice sheets. This is sea ice, total extent of sea ice in millions of square kilometers. And you can read that. The gray lines are 78 to 2007. The blue lines are 2007 to 2016. The orange lines are 16 to 23. And the big fat orange line at the bottom is 2023. So sea ice around Antarctica is at a historic low basically since measurements began. And these are done by satellites. Okay, this paper got a lot of attention when people start talking about sea ice. We did not see emperor penguins. You can't see emperor penguins when you visit the peninsula. Everybody always wants to see emperor penguins, but you can't see them on the peninsula because they don't live there. They live farther south. They live on the ice shelf, attached with the ice shelf. And if you've seen the Penguin movie, you know that they trundle across the ice shelf. They lay their eggs, they raise their young on the ice shelf. And in 2022, the ice shelf collapsed. And in one of those events that got everybody's attention, it drowned hundreds of thousands of penguins, baby penguins, right? If you want to get somebody's attention, say baby penguin. And so all these penguins drowned. And the reason was that the ice sheet collapsed. And so the quote was, first recorded incident of widespread breeding failure of emperor penguins that is clearly linked with large-scale contractions in sea ice extent. So these authors then conclude, this is the future, that if sea ice continues to do what it's doing, no more baby penguins. And that definitely got people's attention. And I just couldn't believe this, but yesterday, this was in the New York Times. You might have seen it. This is a figure from yesterday's New York Times. Ocean heat has shattered records for more than a year. What's happening? So there's the graph there. All those gray lines say all other years since 1981. The yellow line says 2023. The orange line says 2024. Okay, now remember what I said about water under ice shelves. Water under ice shelves ultimately melts ice shelves. And it's a normal thing. So when water is warm under an ice shelf, it melts ice shelves faster. So now look at this cartoon and look at the red arrow. This is a cross section through the edge of an ice shelf. If that red arrow, so this is normal, this is how it's supposed to work. But if that red arrow is warmer than it used to be, then the ice shelf will melt faster than it used to. And all you have to do to understand the previous story is to put a little baby penguin on the top of one of those icebergs there, and you'll see what is going on. Okay, and I just want to leave you with this because this paper was published last week. And again, this is a paper that I was very struck by because it was not normal scientific language. Perhaps some of you have heard about tipping points, and lots of people talk about tipping points with climate change. And when are we going to get to a point of no return, et cetera? These folks don't use that phrase, tipping point, but they do use a more jargony, but basically the same idea. they use the term regime shift. What they mean by that is a change in the way the ocean ice system in Antarctica works that will not change back, no matter what we do, no matter what happens. So this is a very sober, very technical climate paper published in the Journal of Climate, which is not a hotbed of wacky literature. And the punchline is in this little box over on the left. These statistical changes are consistent with theoretical indicators of a critical transition or regime shift, meaning that the entire Antarctic ice ocean system may actually be at what common language calls a tipping point. So if this is really true, then this is much earlier than people were talking about tipping points being reached in Antarctica just a few years ago. So I worked hard on the title of this slide. Places, of course, don't have meaning. We give places meaning. We extract meaning. We manufacture meaning. So when I say the meaning of Antarctica, I don't mean that Antarctica has inherent meaning. I mean, what should we take away from Antarctica? Antarctica, as I hope I've showed you, Antarctica has literally been at the center of the world for the last 100 million years, and it still is. Understanding Antarctica is absolutely essential to understanding the world and how it works. But you can't understand that unless you understand Antarctica's history, how it got to be as it is. You have to understand how the Earth system works in order to understand what we're doing to it. And Antarctica is just such a powerful example of how the Earth system works. And that's what I mean when I mean that Antarctica is both extreme and unique, but also very representative of what is happening to the rest of the world. Antarctica is clearly changing in very complex ways that we're just figuring out, but it's clearly changing, and it's changing faster and sooner than we thought, or maybe hoped. This is interesting and poignant and worth thinking about a lot, because Antarctica is still the least human affected place on Earth. There are traces of human contact everywhere you go in Antarctica, but they're minimal compared to the rest of the world. And therefore, it's so visible, it's so striking that we're changing even this place that is almost unchanged. And then a social political comment, which is that Antarctica is literally, in a legal sense, the only international continent. It has no government, it has no permanent residence, it has no countries, it has no armed forces. It is by treaty, the Antarctic Treaty. It is an international peace monument dedicated to peace and science. That's what the treaty says. The treaty expires in 2040. Keep your eye on that date, because things are changing in Antarctica, and I don't just mean climate. There are 70 bases in Antarctica from 29 countries. They are not all there to do science. They are there to stake claims, to think about resources. Antarctica is a monument to something that doesn't happen very often, which is cooperation. And it's worked really brilliantly for a long time. So Antarctica is not just important as a place to understand how it works naturally. It's important to think about how it works sociopolitically. And I can't give you a talk without showing you penguins. And I thank my wife for taking this lovely picture. Thank you very much for your time tonight. Hope you enjoyed it.
Thank you, Warren. That was great. I'm going to open it up for questions. And you can either raise your hand using the reactions button in Zoom, makes it so that I can see you. And I see Elizabeth.
Elizabeth has raised her hand.
Yes. Go
Hi,
ahead,
Elizabeth.
So tourism to Antarctica is increasing on small boats and very large boats. Is that something that's good because it raises people's awareness? Is it, we know that the treaty protects, it tries to think of the fragile shoreline and by some reservation system keep the traffic down. But so my question is tourism good or bad for what you just told us is happening?
I was afraid you would ask me that question.
You're
I was
welcome.
afraid someone would ask me. That is way above my pay grade. It's an extraordinarily important question. And it's true, and it's an important question for so many places that tourists go today. And all I will say is, having gone to some of those places, is that it's a trade-off. Too many tourists can be horrifically damaging. Too few tourists, and we can't understand what's going on and build a consensus that those places are worth saving. Ecotourism is one of the few industries in many parts of the world that we want to protect. And so shutting down tourism would be catastrophic. But at the same time, tourists have ruined a lot of places. So there is, and like so many things, there is no answer to your question. And so for those of you who don't know, the Antarctic Treaty is quite elaborate in its governing of who can land where and do what. And so far it's worked remarkably well. But we were told there were 60 cruise ships on the peninsula this austral summer. And that's a lot more than there were just a few.
Which I
and we didn't see but one. That is correct.
That was a credit to this reservation system.
They're paying attention. That's right. They paid a lot of attention to it, and you get in big trouble if you mess up down there with that. Galapagos is the same way. But there is no answer to your question, Elizabeth, and that's frustrating.
Yeah, and I think my answer would be yes, as to whether it's good or bad. Yes.
Yeah, that's right. Yes.
Other questions? Bryce.
Who enforces the rules?
Good question. So the treaty states that each signatory country is in charge of managing its own people. So, for example, and via its own bases. So, for example, if you're an American citizen, you cannot go to Antarctica without the permission of the governing body the body that handles U.S. access to Antarctica, which turns out to be the National Science Foundation. Used to be the U.S. Navy, and every signatory country has a system like that. So there's somebody in charge of whether Argentinians or Chileans or Hungarians can go there. And so there's no police force, but it's kind of some enforcement plus national authorities, not letting you do certain things or not letting you go there unless you have a reason to go. You can't, if you're just a private citizen, you can't just go. You have to. There is one commercial airport, or an airport where commercial planes land, but you can't just go there for fun. You have to get special permission to make all that happen.
Other questions? Ingrid, go ahead.
Yeah, I know that the ozone hole has stabilized, but it still isn't shrinking a lot, but it's still quite large. And I was wondering, when you're down there, do you have to take special precautions to protect your eyes and your skin from, more ultraviolet light?
People who are cautious about such things definitely did that, Ingrid. Yes, and of course I'm not. But I'm glad you brought up ozone. I was going to include it, but I had to cut something. Ozone is one of those many complications in the Antarctic story. You all probably know from the 80s that the Antarctic ozone hole was great. The big cause celebre. The penguins are going to get sunburned kind of stuff. And that led directly to the Montreal Protocol, which banned CFCs and other chemicals that damage the ozone. It turns out that ozone is a fixing the ozone hole was really great for UV radiation, but it turns out that ozone is a greenhouse gas. And so some of the warming, there is a hypothesis out there that fixing the ozone hole actually accelerated warming in Antarctica in an unexpected way. So yes, the ozone hole's still there, but it's smaller than it was, which is good news, except that more ozone might be not good news.
Other questions?
What was your favorite part?
What was my favorite part? My favorite part was that I actually got to see it. And everything I read before I went down there, and I read a lot before I went down there, and almost everything I read said, make sure you stop and don't make any noise and just think about where you are. And that was really good advice. And so that was my favorite part.
And Rob's got a question.
Is there any place where, due to recent melting, there are new and important outcrops being exposed? I know on the trip you wouldn't have seen them, but have you heard of such a thing?
I'm thinking. Not that I can think of, but there probably are. It would be on the peninsula. So that's a really good question. I don't think so, but I'm probably wrong.
Thanks.
Any other questions?
I just want to say that if you're interested in learning more about Antarctica, PRI is trying to get more active in providing information about Antarctica, in part because of our collection. We do have some specimens on permanent exhibit at the Museum of the Earth. We're going to increase that, we hope, in the coming months. So if you're interested in Antarctica, stay in touch. We're going to try to do more to increase awareness of our really extraordinary fossil collection that comes from Antarctica and tells a lot of these stories.
I think we've got at least two more questions. Mary Paul had a hand up and Wendy put one in the chat. So we'll go to Mary Paul first. You're still muted. Let's see, can I unmute you? I can ask you. There you go.
Does that work? Okay.
Yeah, we got you now. Yep.
I was just wondering, with all the emphasis on the circumpolar current down there, is that likely to change with and how do you find out about these things anyway? And how do you find out how it would change if it's going to?
Wow, great questions. If you all want to go out and get some food and come back, we'll do another hour on that. So you measure currents mostly from satellites. And that is a great question because we really could talk for a long, long time about this. What the tipping points you read about most in the media have to do with ocean currents. And this is the kind of day after tomorrow stuff that you might be familiar with. We pay most attention to some of the currents in the North Atlantic because they would affect our weather and climate most directly. But all I'll say is yes, there is concern. Not that the circumantarctic current is going to disappear. That'll take millions and millions of years. But that changes will occur in either the generation of Antarctic bottom water as water warms around Antarctica, or a slowing of the ACC might lead to more infiltration of warmer water from the north. Even small things are going to make large changes in the Antarctic. Antarctic water is already increasing in temperature. And we know that not just from measuring the temperature of the water, but by looking at the organisms that are now successfully invading from the north. We now know that species are naturally coming as the water gets warmer, and that's going to change ocean ecosystems. So that's probably going to be the first things that we'll notice. I hope none of us live long enough to actually see weakening of the ACC or of a generation of Antarctic bottom water. We'll probably see things in the North Atlantic happening before that. But yes, these currents are going to change. As temperatures change, these currents are going to change. It's just a question of how much they change.
Oh, thank you.
Wendy's question in the chat is, Warren, if you had an opportunity to step a bit away from the group, what were your senses experiencing? Smell and sound were your senses?
Penguins stink.
Hey.
A lot.
One man's
They
opinion.
stink a lot. That's a great question, because I mean it's really cold, it's really windy, it's really bright. It is a complete sensory overload because of all those things. I've spent a lot of time in tropical rainforests, and so this is a weird thing to say, but that was the closest feeling.
Not weird.
When you step into a tropical rainforest, most people describe it as entering a cathedral. Antarctica is not like a cathedral, but it's that kind of shock and awe kind of feeling to it, and I suppose that's the best way to describe it. And that never went away. The 3 weeks we were there.
Thank you for sharing that, because that is a very human part of the component. I'm a geoscientist, and my husband had a chance to be part of those NSF support groups that helped researchers down there earlier in his career. So he did several stints at McMurdo. Well, really long, hard days, and getting on a C-130 or something out of Christchurch, New Zealand, and flying most of the way on a 9 or 10 hour trip to have to be turned back 50 miles from landing because weather conditions couldn't support landing. So he had a very different sensory experience. And I wanted to hear yours in that more calmer, exploratory
Can I add my sensory?
Sure.
Yes, please.
So my takeaway is it was so much quieter and so much emptier and so much bigger than I can really find good words for, and I'm a pretty chatty person, but that was the awe that I felt. It was hard to find words for empty, quiet, blue.
Big.
Wow.
And we didn't even see the big part. Your husband saw the big part.
It's from the back of a little plane collecting geophysical data, but yes.
Right. People who've been to the South Pole and McMurdo describe everything I've said times 100.
Yeah, I can feel that. Well, thank you.
Thank you.
I have one comment on that. I've spent a little bit of time in the Himalayas, and it was the same kind of how dominant the environment is around you and how little you are in that space.
Yes. Littleness. Yes, absolutely. Which is one reason to go.
Yep.
You guys have given me chill bumps, goosebumps with thinking about the beauty of the earth. So even when it's perilous.
Wow, it works. Awesome.
All right. Well,
Thank you.
We're about 8:30 and time to about call it a night. Join us again in 2 weeks for learning about how we can save whales to help whales save us. And then on our last session on May 9th to hear about the ocean's mysteries unlocked by the JOIDES resolution and experience for educators particularly.
Don't miss that one.
Yes. And thank you
for
all so
tonight.
much for joining us. And
Thank you all
for the great talk.
Thank you.
Good night.
Thanks.
Thank
Well.
you. Yeah.
Bye.